Hi folks, Dragos here from the Senior Dev, and today, together with Bogdan, we're gonna go to some of the hardest and weirdest JavaScript interview questions that even senior devs can't answer. First question, Bogdan, can you explain tail recursion in the context of the event loop? And how is it useful in JavaScript?
Okay, so let's talk about tail recursion. So basically, tail recursion is when the last call in a recursive function, it's a call to itself. To give a quick example, you can imagine maybe inside a framework like React, we have our render function that will take some components and render them. But we do know that the last instruction there will probably be another render to the children of that component. So that's a recursive call, right? And probably in between, we would have some instructions. In certain programming languages, the compiler would allow you to optimize this. If you don't optimize this, the memory complexity of the stack memory would be ON. So let's write it down here. So basically I'll have an ON where N is the number of recursive calls you're making. The problem is if N is very big, you will run out of stack memory. That's what we call stack overflow. Let's make this blue. This is our stack. And so every time you call a function, you push what they call a stack frame, which is a self-contained segment of data, including the code and all the variables that you need to execute. So it all sits in the stack until you basically execute that function and then you pop it out of the stack. So you're going to have a lot of those, right? When React renders like a big application. And so what will happen is that if you keep adding, right, if your recursive chain, it's bigger than the stack, you will run out of stack memory. And that's what they call stack overflow.
Finally, the famous stack overflow.
Exactly. And to avoid this, there's an optimization you can make where, to put it simply, the compiler will, because there's no real difference between calling this function in between in the code in the stack frame except for the arguments. And the way you can think about it, it's basically when you have tail recursion, what the compiler does is that it just saves the reference to a single stack, and in a way it will be reusing that same one with different arguments, but it doesn't store this again and again. So it's just going to use a single one. And so all of a sudden you go from ON to O1. But there's a magic condition, which is it can only be done for functions where the last instruction, it's a call to itself with different arguments.
Is tail recursion something that we actually use in JavaScript?
Well, it very much depends on who implemented the JavaScript execution engine, and it's different in Node.js and it's different in all the different browsers. I think as of today, only Safari implements tail recursion. The good news is, again, it's very much of an edge case. It's not something most applications will use. But as of now, only the Safari browser implements it. Because again, JavaScript, those things depend on who implemented the engine that will actually execute JavaScript.
Bogdan, you have a point. This is quite of, tail recursion is quite of an edge case in the current JavaScript landscape, but we've seen more and more concerns about JavaScript apps getting bloated, too much code, too much useless stuff going on. So I think this kind of edge cases are becoming more and more relevant if what we want is performant apps in 2025 and beyond. By the way, if you are interviewing right now, or if you're simply looking to get to the next level as a JavaScript engineer, the best way to start is by understanding what your technical gaps are. Check out the free technical assessment in the comments. It's going to take you about 10 minutes and it's going to give you a full report on what are the things you need to improve for you to perform better and to get closer to the senior level. Question number 2, how does garbage collection and memory management work in JavaScript?
Okay, so garbage collection and memory management. Maybe I can reuse this drawing over here. We do know we have the stack. In JavaScript, we basically have the event loop that will look at the stack and keep executing that. But we also have a large section of our memory, like another type of memory. The stack memory, it's what the kind of the CPU, the processing unit of JavaScript will use. Perfect. So that's our kind of processing unit. There's more elements, but you can think of that as the event loop. And of course, this works in combination following the von Neumann architecture. It works in combination with our memory. And I'll call this what they traditionally call the heap, which is unstructured memory space, usually allocated in your RAM memory, in the random access memory that the computer has. And so whenever you interpret some piece of code, you'll find data like objects, and you are going to allocate space, right? So let's allocate some space. We read our program and we start allocating different memory segments that are being used in our code. So we store an object here, then maybe another object, we put an array here. What usually happens in traditional languages like C# is that whenever you allocate a variable, you need to say how much it will occupy. In JavaScript, to make things easier for us, the developers, the language kind of tries to guess more or less how much space it will allocate. And then whenever you go over that, let's say you have an array and you add more things to the array, then the language will automatically resize the array and relocate. Now, because that happens, it will also try to garbage collect. It will try to clean up the allocated memory when it's not being used anymore. So imagine in your code, you're using this huge array, and now that kind of, you're not referencing it anymore, you don't need it anymore, then the garbage collection algorithm that runs periodically will try to say, hey, this memory space is now free. So you can place things kind of on top. We never delete from memory. Like, you can just place things on top. So basically, garbage collection, it's an algorithm that internally all the JavaScript runtimes have, and it will basically run, every once in a while and try to free up memory. The problem with JavaScript is that you have closures. And closures mean that if you have a function, right, and it's attached to an event handler, or is being referenced, right, so that function we can't really delete, we'll keep, and usually we store it also in the heap. Now, this function encloses some big variables. Let's imagine you declare this function, and in the same scope, you also have a reference to some big array. Let's imagine you're referencing this, and then you also reference this, and you reference this. Maybe you don't really need them, but you somehow enclose them when you declare your function. And so all of them are somehow needed, right, as dependencies, because they're being enclosed in the lexical scope of this function. So that memory cannot be released when you run the garbage collection algorithm. And what will happen if you have enough of those is that you run out of heap memory. And this is why if you use any modern application, you'll see that even Google Meet in the browser cannot work without 400 megabytes or something along those lines, right? At the very least, I sometimes had instances when I had a video call and it took over 1 giga of my RAM memory, which is crazy. I mean, computers didn't have 1 giga RAM all the way up until maybe 2010 or 2015 or so. I mean, memory is very expensive. And because of closures, and JavaScript is not a very memory efficient language, no matter how much they try to optimize garbage collection, you got to make sure that in your code, you don't abuse closures, because closures have a huge memory cost.
I think Google Chrome implemented a feature where you can just hover over your tab, and it will tell you how much megabytes or gigabytes that specific tab, that specific application it's using through your browser. And for me, it was the same. It was pretty surprising to see some apps, some web apps, taking up to 1 gigabyte.
Do you see when I hover? I just did it because you mentioned it. Do you see when I hover?
I don't see it.
I do. So I guess it doesn't show you the overlay, the screen sharing. But right now, this drawing application, TLDRAW, it's using 500 megabytes of RAM memory, and this other one, which is my code sandbox, it's using, and I think it's silenced, it's like Sleepy, it's using 250. So that's already 700 megabytes for only these 2 tabs.
Keeping in mind that the average developer has about 55 tabs open at any point, then we're definitely going to run in memory management issues. Okay, Bogdan, so the point is closures are quite inefficient because you're passing this scope all over, but why do we even use them then?
So the reason why we like closures is because it's just easier not to have to pass, imagine all those things. Let's imagine this is A, B, and C. If I do not have closures in languages where you don't have closures, you need to pass this as arguments all the time. And so your function signatures become much longer, and it's just a lot more tedious programming, especially for things that are constant. So usually imagine A, B, and C, they don't really change. They're like global settings, but you need to use them in a function. If you don't enclose them, you need to pass it as arguments. Of course, you could unify this in a single object, but then it would have 3 properties. And so it simplifies function signatures at the expense of using more memory.
Understood. Bogdan, on to question number 3. What is a generator function in JavaScript? Could you write one right now? And why would you use one in the first place?
Sure, let's try and write one. I have a code sandbox here. So you mentioned generator functions. So basically generator functions are functions that you call, and they will give a different result depending on when you call it. And so as a developer, I can actually build one. So let's say a function alphabet. And so this function, whenever you call it, it will keep giving you different letters. So let's say it will first return, which we call yield here, the A, and then if you call it again, it will yield right, B. So it has kind of an internal state, and depending when you call it, and then it will yield a C, and finally, let's say we return a D. And so whenever you'll call this, it will give this different, it will create sort of an iterator. So basically we call these letters, let's say, and that's equal to an instance of alphabet. This is a very simplified example, but now I can actually, let's console log the letters dot next, and that's how you basically use them. And so whenever I call them, I'll get a different letter until it stops. So let's log this. And do you see my console?
Yes, I do.
Perfect. So as you see, it was first a value A, and it gives you this done property, which is false, then B, C, D, and finally it's done. It finished. So when you call a generator function, you get back an iterator, kind of a structure that implements the iterator interface in JavaScript. And you are able to call that all the way until done it's false, done it's true, and you get all those different results. So it's very good to mimic certain behaviors. To be very honest, I haven't used it too much in production code bases, but it's actually used to create the async await syntax sugar. So you can use a combination of these functions and promises to actually translate async await. And that's why we say that async await is only syntax sugar. You can find a more detailed explanation of this. I do not think I can write it up on my head, but you can think of it as every yield would actually be whenever you write an await. And what it will actually do when you have an await is that this function will end up kind of calling itself, but of course, it will go to the next yield. That's why whenever you finish an await, so basically what an await would do is to call promise.resolve. And when a promise is resolved, because when you put await, you're actually waiting for a specific promise. When that promise is resolved, you recursively call this function and it will go to the next yield, which would be the next await. This is a very rough explanation, but that's how async await actually works. And it's only syntax sugar. It's not a language feature in itself. It's literally just translating your async and await into a recursive generator functions that works with promises under the hood to actually give you the asynchronous behavior while you write code that looks synchronous.
Is there any other use case you can think of where generators would be besides the async await syntax sugar?
Sure. So you can use generator functions to make all kinds of funny things, like, for example, an infinite counter. So normally when you create a counter function in JavaScript, you need to somehow have a counter outside here. We do that. And then we will have a function, and this is called count. And basically it will increase the counter. So we make counter plus plus, and then we return it. The count. Whenever I want to increase the counter, I call this function, it will increase counter and then count again. But as you see, this variable, it's enclosed. So it's a lot easier if you have a generator, and you can call this create the counter. And basically what we want to do with the generator is that we initiate that inside the function, which is a lot memory efficient. Looking back to our discussion on garbage collection. So we have our counter, and with the generator, we just want to keep returning while true. So because they don't go on, it will only be invoked if I call it again, right? So this is not an infinite loop. And then I can say increase the counter and then return it. Return the count. And so let's create it. So I can say constant counter. It's equal to my create counter. We could even have an initial value if we wanted, but let's leave it as it is. And then I can just console.log our counter. So this is our counter dot next. So every time I call the next method, I get a new count. Let's call it a couple of times. Okay, so this would be a yield, perfect. And now it's going to work. Yeah. And I can do this until 1,000. So I managed to somehow have an infinite counter. I mean, this is a very simple example, but you can use it for all kinds of functions with sort of an internal state, where you can have an internal state and modify that. And then every time you call it, it gives you the next value.
Well, enough about generators for now. Question number 4, and this question is about array.sort, the array method. What would you say is the time complexity of this array method? array.sort.
That's a tough one. So array.sort, and this will basically get a sorting function and return the sorted array. If I recall well, JavaScript uses what they call team sort, which is, I think it's a combination between quick sort and insert sort. What I do know for sure is that the time complexity of this, the average one, so the average one would be n, which is great, and the worst case scenario, no, the average is n log n. I think the best case scenario is n, which is amazing for so best case it's n, the average is n log n, and the worst case it's n log n. So that's pretty much, it's a variation of sort that's pretty complex to implement, and it's a combination, I think, of insert, sort, and quick sort. But yeah, there's like thousands of sorting algorithms out there. I think most JavaScript runtimes implement team sort. Definitely V8, which is the Chrome engine for JavaScript, implements team sort.
Is there any other sorting algorithms do you know about, Bogdan? And which would be your go-to quick solution if you had to use one?
So if I had to implement one, I'll probably start with the simplest ones, which is selection sort. In selection sort, it's pretty bad performance-wise, but in selection sort, you would connect array to the array, and you look at the right-hand array and pick the minimum. You compare the minimum with your current element, and if the minimum is lower than your current element, you swap. So it's super easy, right? It's just finding the minimum, and you keep going that, but it has an n square, right? It's n by n. And then there's like this bubble sort, where you go to the array and you just swap elements with the next one. So you compare, it's double B. So you compare the current element with the one in the next position, and if it's smaller, you swap. You need to do a couple of runs to sort the whole array, and so it's also it's not very memory efficient. There's merge sort, which is recursive. There's insert sort. So there's just so many of them. If someone would tell me implement a sorting algorithm, I'll probably start with the simplest one that I remember. And in my case, it's definitely selection sort. And after that one, there's the bubble sort, which are very easy. And after that, I'll look at merge sort, because I know that solution is recursive, but I know it kind of splits the array and there's a base case and then you put it together. So I probably could work my way through it.
On to question number 5 and final question. Have you heard about object proxies in JavaScript? Can you give a real-life example where they are being used?
So as the name says, it's a proxy, and proxies are always things that sit in the middle. So that's our object. With the proxy, instead of giving the actual object to the user, you can think of it as we wrap it in a proxy. So we basically are wrapping it in this fancy proxy. And whenever the user will call into this object, we have the opportunity to add getter and setter functions. So we could add some logic in here. Let's say, imagine this is our logic to do things before we call into that object. So when I make a get or a set, I go to that blue box before I actually get in return, right, the value. And so, yes, exactly. Now it's actually working perfect. And so it's the same, right? This would go into that, but go to our proxy. Like this is a proxy logic. So I think one of the best use cases is to implement something like state in React, like reactive state, because you could actually create a state object and this is our value. Let's imagine this is a counter. And so whenever people want to update that counter, and in React, you do that with a set state. So you create your state object and then you update that. Whenever they update, we could actually make the update, but then in our blue logic, make sure we also trigger a re-render. Now, that's not exactly how React does it. It's a lot more complicated under the hood. But if you tell me, Bogdan, implement reactive state in 2 minutes, I'll probably use a proxy object and I will create a create state handler, and that create state will take whatever initial state you give it and give you back some setter. But in reality, when you call that setter, I will in the background also run all these functions. So basically, when you create a proxy, just to show the code, you would do something like new proxy, and then you pass in your state, and then you'll have your handlers. So basically, whenever you want to create a state object, I'll actually run the proxy and pass in my own handlers. And basically the handlers are basically functions that look like, for example, set, where I think you get like the key, and then the actual value, and then the next value, or something along those lines. I will have to check the reference, but this would allow me to, in my set function that I define somewhere after I do the update. So I just say, the state or the key you gave me it's equal to the new value. This looks exactly like a normal object update, but here I can actually say re-render, and I would be able to create reactive components or state with basically native JavaScript APIs by using proxies and wrapping those state objects.
Well, there is a bonus question though. We are not done yet. Finally, I wanted to ask you, is there any upcoming JavaScript feature you are excited about?
I mean, there's a lot of low-key features that are cool but not super interesting, but I would say the best one that I'm looking forward to, it's signals. And basically signals allow you to natively create what I just mentioned before, which is reactive state or reactive variables in plain vanilla JS. So you don't need React or Angular or any of that. You can literally subscribe in vanilla JavaScript to certain values, and then they would automatically react or update or re-execute certain code when the value updates. So it's basically implementing the observer pattern natively in JavaScript. And I think it comes because it will really eliminate a lot of the overhead in terms of frameworks, and it will give a lot of power to vanilla JS. This is still in early consideration, so maybe we'll have to wait another year or maybe 2 years for it. But I think frameworks will have to be redesigned, because all of a sudden the reason why you needed a framework like React or Preact or whatever was because you wanted to have reactivity. But if you have that in vanilla JS, then you all of a sudden can just do a lot of things with vanilla JS, especially now that we also have components and imports. So I love the fact that a lot of the features that were battle tested in modern frameworks now get added natively to JavaScript.
Amazing, Bogdan. I mean, this seems like a very innocent question, but it's very important in technical interviews that you have something like this prepared, right? Because it's a very crowded market out there, right? Everybody knows React, everybody claims to know JavaScript. And this is a very good way to not just tell, but show that you actually care about your craft, that you actually care about where the JavaScript ecosystem is moving, and you do your best within your daily job, of course, to stay up to date. Okay, folks, Bogdan, as always, thank you so much for the amazing performance. And for everybody watching, by the way, if you are interviewing right now, or if you're simply looking to get to the next level as a JavaScript engineer, the best way to start is by understanding what your technical gaps are. Check out the free technical assessment in the comments. It's going to take you about 10 minutes, and it's going to give you a full report on what are the things you need to improve for you to perform better and to get closer to the senior level. With that being said, thank you so much, folks, and we will see you in the next one.